All right, let's get started. Good morning and thanks so much for joining us today. I'm very pleased to be joined today by two great engineers from GHD who are power users in InfoWorks ICM. The GHD team have two projects for you that will cover how calibrated models are being utilized to understand the long-term performance and frequency of overflows in sewer networks. So sewer overflows are topical at the moment, as we're all aware, with heavy and severe rainfall across Brisbane, the Gold Coast, southeast and western Queensland, and what news outlets were referring to a 1 in 100 year event across Sydney and New South Wales. They've brought significant flooding and overflow events across those particular regions. The first of the two projects, long time series modeling of overflows, highlighting GHD's work with urban utilities out of Brisbane, Australia. And the second of the two is a 50-year time series assessment of sewer network models, highlighting GHD's work with Melbourne Water for Victoria. So I'm personally looking forward to paralleling these two projects for the respective regional considerations from a climate and design standards standpoint, and then to look at the commonalities in the studies as well as to contrast them. I'm Patrick Bonk, a software solutions lead with Innovyze, and I'll be hosting today's presentation with Nicholas Dahl. And Nicholas is a civil engineer working primarily in sewerage network planning at GHD in Brisbane. He has a background in wastewater treatment and computational fluid dynamics and holds a PhD in wastewater treatment and waste stabilization ponds. Nicholas has been working with GHD for 4 years and closely with urban utilities and other councils and utilities to develop, calibrate, utilize hydraulic sewage models and develop bespoke uses for them. I also have Jonathan Orr with us today, and he's a technical director, wastewater at GHD. He has been working in sewage planning for 20 years for many clients across Victoria and around the country. So before we get into it, we're really grateful to have you join us today. We've written today's session to encourage lots of questions and interactions with you, the listener. We'll be taking questions on the fly, so please enter your questions in the dialog box that you can see on your screen in the webinar pane, and take this opportunity to gain insights from two of the best industry experts on this particular topic. So let's get started. I'm going to hand it over to Nick, who will speak to the first of the two projects, long time series modeling of overflows, highlighting GHD's work with urban utilities out of Brisbane, Australia. Over to you, Nick. Thanks so much.
Thank you, Patrick. So this work, we're looking at two catchments that are operated by urban utilities, referred to as the S1 and S2 sewerage catchments. They're shown there in the figure, S1 in the north and S2 in the south. And what we're doing is running a long time series of rainfall events across these models. And we're utilizing calibrated models. So I've just listed out some statistics against each model just to give you an idea about how large the models are. So you can see there 70,000 nodes and 50,000 nodes for the two catchments. And we're doing the modeling on an all pipes model. So that's all of them. And I've got quite a number of overflow structures for possible spills. Next. Patrick, thanks. So the project objectives, really at the core, we want to understand what the performance of these catchments actually are. And we want to use real rainfall that's been recorded over these catchments to test the frequency of spills, how many spills, volumes, and etc. And then secondly, we want to be able to identify suitable rainfall events that we can use for future containment planning. So that's like the master planning. So instead of using design storms, we can use real recorded storms that give a certain level of spilling and design our containment to those. Next. So really at the core is the long time series model. So the long time series is really the rainfall. And so what we were given for Brisbane was 30 years of rainfall data that Brisbane City Council had collected. And so at the outset of the project, we decided, roughly 10 years would be a representative timeframe. So we looked at this data in the first 10 years of the 30-year record. There weren't very many monitors operating. The data was quite sporadic, lots of drops. So we kind of had to discount that. The next 10 years was the millennium drought. So it's probably not that appropriate to run and test overflows against. So really that left us with the last 10 years, which was the period of 2008 to end of 2017. And we analysed the rainfall across this 10-year period, and we pulled out each of the events. So, and we did that using general thresholds, like minimum of 10 mil in 12 hours, just to get all of the different events. And we decided that we would merge events that were in close proximity, so say within 3 days of each other, into a single rainfall event. And we did that because we weren't sure with the overflow structures if they would actually come back to dry weather conditions. Complete dry weather conditions, and so if we start the next simulation too soon, we might be resetting the conditions. So after analysing that, we ended up with about 200 events, and we did this twice, once for the S1 catchment and once for the S2 catchment. And it's important to note that we were using about 40 gauges in the S1 catchment and about 12 gauges in the S2 catchment. Now, we don't want to have to run all of these rainfall events, because once we get down in the rainfall depth and size, we're looking at like 30 mil, 20 mil for an event, and the overflows are going to get quite small. So we prioritized the top 120. And from the outset of the project, that was just an estimate of how many there would be. So the longest rainfall event actually ended up being 50 days. And that's because it rained and then it stopped, and 1 or 2 days later it started raining again, and it just kept doing that. So that ended up being what we call one event or one sequence. Next. So the process. So what we're doing is we're relying on a calibrated hydraulic model. So these models were calibrated to temporary flow data and temporary rainfall data. The calibration is about 3 years old. And what we did was we took those rainfall events that we just defined, and there were 120 of them, and we ran 120 simulations. And we started each one up manually, as shown in the figure. And all of the initial conditions, so the groundwater was set specific to the start of each rainfall event, obviously using the preceding rainfall event. Next slide. So now that we've run the simulations, we've got results. So the first thing to note is that for the S1 catchment, there was about 1 terabyte of result files and 0.5 terabyte for the S2 catchment. So what we could do, so firstly, what we can do is look at all of the assets that spill at any point over those 120 simulations. And for the S1 catchment, it's about 650 and 530 for the S2 catchment. And we excluded the small reticulation because when running large ARI rainfall events, it's not the most practical thing to include the reticulation. So with the results, we analysed it in 2 ways. So we had the frequency of overflow per asset, and secondly, we had the ranking of the overflow that occurred over the whole catchment for a set period of time. So the first piece of analysis, is shown in the two images to the right. So the top one, I've just pulled out an example asset. So each point on that graph in the top represents a spill. And they have various volumes of spilling and they occur at various times. So over the 10 years, which is our representative rainfall time period, this asset spilt 85 times. So if we say 10 divided by 85 and then times by 12 to get into months, we end up with 1.4 months of recurring spills on average. So it gives us an idea of what the frequency of this specific asset is in terms of spilling. And we can do that we did do that for all of the other assets that spilt over the entire 10-year period. And the distribution is in the bottom figure. So you can see that the left-hand side of the figure, we've got close to 0 spills, so start at 1 spill, and then the number of assets on the y-axis. And so there's quite a number of assets that only spill once or twice. So their containment is at 1 spill per 10 years or 1 spill per 5 years if they spill twice. And you can see there's an elbow at about the 10 spill count. So the assets there have a spill frequency of about 1 in 1 year. And then it tails down towards the 50 spill count. And then there's a couple of assets that spill very frequently. And they go into the order of months. So staying on this idea of how frequently assets actually spill, we can use that information to inform operations and get an idea of how the network performs. Next slide. So what we did is we calculated what the spill frequency was for every single asset and put it on a catchment map. And we put the sewer network pipes in the background, and it highlights where the really frequent spills are, where the points on the network that spill are. So in this figure on the right, the model predictions are in different colors. Aerostructures are squares and manholes are circles. And what we can do is we can overlay the utilities, in this case urban utilities, wet weather overflow cleanup records. So the overflow cleanup records are shown as the green circles on the figure. And where we get some similarity between model predictions and their records, it gives us confidence that there is a problem there. So for instance, on the figure, there's a big red circle near the bottom. So that's an aerostructure that operates frequently in the order of months, and there's quite a number of wet weather overflow cleanup records situated at that location. So it gives us confidence that there is something wrong at that point. This really also helps us highlight where we're perhaps not so confident or we need to further investigate. So the big red circle in the top left of that figure, there are model prediction spills that spill quite frequently, and they're in a place that the public generally wouldn't go during a rainfall event, and so there's no record of overflow cleanups or reported customer complaints, but the model is telling us that there's a problem. So we can highlight that for future investigation, perhaps put a depth level logger in there and record some data and see if that is, if the model is accurate or whether it needs further calibration. And the other thing that we can do is with the red circle on the top right-hand side, there's quite a number of wet weather overflow records, but it's primarily modeled by a single aerostructure. So that's the red square. And you can see that there's a creek running right next to it. So it's quite possible that the creek level is actually higher during a rainfall event and stops the aerostructure from operating. And that would cause further surcharging and possible manhole spills. So it kind of helps to highlight where some of the assumptions might need to be worked on and how to improve models and where to target further investigations. Next slide. So returning back to the second objective about choosing rainfall events for possible inclusion in master planning and containment simulations. What we had was the 120 simulations of data, and we can see all the spills that occur in them. Now, because some of these rainfall events are quite long and really include multiple rain bursts that create multiple overflow events, what we've done is we've taken those simulation results and we've split out the overflow events from within them. And so the figure in the top right just gives an indication that was one simulation, but there are 2 rainfall events and 2 spills. So that's the hatched area. So we went through and did that for all 120 simulations, and obviously the number of overflow events was slightly more. And it's important to note that the time that this applies to is consistent over the whole network for an overflow event. So we're no longer looking at individual assets, we're looking at what happens at the network level. And so what this does is, if we do that and we take the volume of spill from the entire network over that time range, we get a table, and we can rank that table. Largest spilling volume from the network as rank 1, and then descending down. And that's what the bottom figure shows us. So the bottom figure is a distribution. So on the x-axis is the rank of the overflow event. The black line is by spill volume, and the blue line is by the number of assets spilling in that event. So really what this says to us is that the black line, at about the 10th ranked event, there's an elbow. So ranks 1 through 10, you can see there's quite a steep line. So the volume that's spilled in those events just gets higher and higher and higher. And really, if we're looking at containment standards, that's probably not a suitable place to be. We want to be down further where it's more reasonable to contain the volumes. So, if we take the 20th rank event, for instance, so that is so on average, that is 2 spills over the 10 years, which is about a 6-month recurrence, and then 40 overflow events over 10 years, that's at the 3-month spill recurrence. So what we can do is we can look at the rainfall that actually created that spill, and we can say, nominate that rainfall event for possible inclusion in master planning. Next slide. So how we use this information. So in the table down the bottom, I've just pulled out some representative rainfall events and the overflow event. So at the 3-month spill ARI, or the 40th ranked overflow event by volume, there's about 6,000 cubic meters spilling, and the rainfall depth is about 65 millimeters, and it's a half a year ARI, so 1.1 in 6 month rainfall ARI that's generating that volume of spill. And we've got different statistics for different spill recurrences. And it's quite interesting to note the box plot in the top right hand corner. So because these overflow ranks, we've ranked them, but the different rainfall, how it comes in the spatial distribution, the temporal distribution can be different because we're using real historic rainfall. We don't want to limit it down to one rainfall event. So we select a few either side. So for the 40th ranked event, we might select from rank 43 down to 37 and look at those rainfall events. So for a spill ARI of 3 months, we're looking at about the 6-month rainfall ARI that generates that level of spill. And for the 6 month, we're looking at about a 2-year rainfall ARI and so on and so forth. So how this information has been used is firstly, helping operations go and investigate and find out what's going on in their network. And then secondly, Urban Utilities has taken this information and has nominated a containment standard to use and taken some of these rainfall events and are now planning augmentations and containment using these specific rainfall events. And the idea is that if we contain the volume of spill that we've observed here from the calibration model, then any lesser ranked overflow event, so lesser volume, should be contained by default. And that will, and if we ran the 10-year simulations again, so the 120 again, we should find that only the events that rank higher than the nominated rainfall event spill. So that's how it's been used, and that was our process. I'll hand back to Patrick now.
Thanks, Nick. We've got some questions coming in, so we'll just take a couple minutes to answer the first couple questions. Nick, do you have a list of all the ARIs against all the rainfall events?
Yep. So as part of the first part of this project, looking at all the events for the rainfall and splitting them out in terms of time, we calculated various statistics, and that included the ARI of the rainfall. And we did that for every single monitor as well, because obviously there's more than just one rain gauge within an event.
Okay, great. In terms of frequency and volume of spills, how do you compare the time series results from ARNR 87 to ARNR 2019? Do you have that off the head?
So we did not do that as part of this project. I did a small test just for fun, and they at least in the response, it looks similar. But I haven't gone into it in enough depth to say.
Okay. Do one more. What assumptions and setup did you assume for boundary conditions and pump station operations?
Yeah, so we purposefully made the decision at the outset of the project to run the calibrated model with, I guess, ideal conditions. So some of the pump stations are operator controlled in wet weather events, and they do funny things. So we made the decision that we would run it as it was designed to be run. And the idea there is if our model predicts X amount of spill, then if they run it in a less efficient way, then it's only going to be worse. So it kind of gives the justification to fix other stuff first and then look at the network results. So the pump stations, we did ideal operations. EROS structures, we decided to leave off any boundary conditions and let the EROS structures spill. And we had, there are no upstream catchments for any inflow.
Thanks, Nick. I'll pass it over to Jonathan now, and he's speaking on the second of our two projects, a 50-year time series assessment of a sewer network model highlighting GHD's work with Melbourne Water in the state of Victoria. Over to you, Jonathan. Thank you.
All right, thanks, Patrick. So the project I'm talking about is again, it's a time series analysis project on the Melbourne Water trunk system. So from the map there, shows sort of basically all the sewers within Greater Melbourne. So all operated by Melbourne Water. So so for those who don't know the Melbourne system, there's three retailers who have the customer interface with the households, and Melbourne Water runs basically the trunk system, so all of the larger sewers. So this assessment is on that trunk system of all the larger sewers, and it's obviously it's a fairly large system. Next slide. So the objective of the project was to produce an events-based analysis and compare that with the time series that we're doing here. And the outputs of that would be to compare the treatment plant wet weather inflows with the event-based flows, and also the spill points and the spill volumes that we get throughout the system. Next. So to define our long-term time series, so we wanted to use 50 years worth of data, so going back to 1960. So I mean, as sort of Nick highlighted up in Brisbane, the older data wasn't quite as good. So we used Bureau of Meteorology daily records dating back to the 60s, and then Melbourne Water had records going back approximately 30 years. And so the data series was produced to generate 30-minute time steps for the data going back to the 1960s. So there was data processing that was done on the information that was available from the combination of the Bureau gauges and the Melbourne Water gauges, and then the data from the Bureau records created 1,020 grid points across that Melbourne network. So yeah, so if you've got 50 years of data with 1,020 grid points with half-hour intervals, you've got nearly 900 million data points. So that was used for the system assessment, and then to apply the hydrology, we just used daily rainfall and evaporation, which was just on a daily process. So we used that as a single rainfall file within the model, whereas for the individual years we did 1 year at a time across the different decades. All right, next time step, next slide. So this was done a couple of years ago. We'd initially planned to use the time series database for all of this data, but at the time we did it, we couldn't quite get it to work as we'd wanted it to, and so we sort of abandoned that idea and went with the sort of the more traditional importation of the rainfall files. Next. Just back one. So yeah, so we put the rainfall files in. So there was as I mentioned earlier, 1,020 rainfall profiles, and so we needed to manually assign them to the subcatchments that we had within the model, and ditto with the evaporation profiles, of which we had about 6. And so that was the rainfall input into the model, and then we go to the next slide. And so yeah, so to get our initial sort of groundwater condition, we ran the daily rainfall file from 1960 to 2018 to generate the soil store depth throughout that whole time series of almost 50 years for each of the subcatchments, and then to use that as the initial condition for each of the rainfall events that we used. Next. And so the soil saturation, as I mentioned before, so we'd use that 50-year hydrology file that we did, and we went to the start point of each of the events that we wanted to look at. Extracted the results, processed the data, and then imported it into an Inferworks groundwater infiltration module file for each of the events that we were going to look at. So that was the process that we used there. And so obviously a lot of data processing, but it seemed to be the most efficient way at the time that we did it. Next. And so in order to select the events, so we had 50 years worth of data. And so initially we selected 70 events based on the rainfall depth from each event. So we thought we'd sort of start with the yeah. So that was the starting point. And for the 50th highest ranked predicted 50th highest ranked events, spills were predicted at 2 of the known sort of capacity constrained parts of the system. And then so that was the top 50 events from the 50 years, and then the next 20 events that we ran, spills were not predicted at those 2 sort of known sites. And so I think probably if you can crunch your numbers in your head, you'd probably sooner be walking along the creek in the rain in Melbourne than you would up in Brisbane. Next slide. And so then in order to check that data off, we had a look at the last 25 years of ERS spill data, as well as the last 20 years of treatment plant inflow data for the 2 plants that operate in the Melbourne system. And what we found out was that there were some ERS spills that were not captured in those top 70 events. And so because of that, we changed our event selection criteria, because obviously there was some spills at some of the events that weren't on the highest amount of rain over the average of all the gauges that we had. And so we adopted a maximum 2-day rolling average for the rainfall depth across the gauges, and added some more events to the list. Next slide. And so our criteria were to include obviously we had our initial 70 largest events, and then because we had the ERS spill data for dates, we included those if they weren't already included in the top 70. We looked at the treatment plant inflows and got the peak flows from the top 30 events. And so if there was any high flow events at the treatment plants that weren't included in that top 70, we included those as well. And then any alternative storm that we identified just as a sort of a coverall. So next slide. So we ended up with 92 events that we needed to look at, or that we simulated, and so we went that. So we sort of got those 92 events, and so as I highlighted earlier, we generated 92 groundwater files for each of those for the starting condition. And so we ran the events to analyze the spills. So at one of the spilling locations, and so for each spill location, each storm was ranked based on the spill volume at each individual location, to determine the spill frequency and the spill volume with a 5-year return period, or a 1 in 5. And so the example that we've got here, so this location spilled for 12 events across the 50 years. So it gives a spill frequency of 4.17 years. And the spill volume with a 5-year return period is 66 kilolitres, which is that sort of the 10th one down there on the list. So so that was one point in the system that had spills and is known to have spills. Then we go to the next slide. And then an example of a second point within the system, which across the suite of storms that we looked at, this site spilled twice, so it's got a spill return period of 25 years, and therefore the spill volume with a 5-year return period is 0, which would be the 10th ranked storm across the suite. So we just go to the next slide. And so one of the things that we wanted to do out of this project was to compare the time series results with the results that we would get from our normal event-based AR&R assessments that we did. And so of the 10 locations across the network that we're getting spills, there was generally some pretty good correlation of the two. And then there were some sort of slight differences in some of what we'll call the sort of the borderline cases. So, you know, location number 8, so the time series didn't predict a spill and the event base predicted a very small spill of 2 kilolitres. And location 10, the time series predicted a total spill of 3 kilolitres as opposed to a spill or no spill in the events-based one. So I suppose a general observation across the events that we looked at was that the spill volumes were generally less for the time series analysis, and that was especially for areas with a very large upstream catchment. So location 2 there has a you know, it's almost double the spill volume in the events-based process. And that area there has a huge upstream catchment, and so probably the main difference there is in the variability of the actual rain from the time series versus the event-based rainfall file that we use for the event-based process. Next slide. And then another outcome that we were looking for in the process was to look at the inflows into the 2 wastewater treatment plants, and we ranked them highest to lowest, and then determine the peak flow with a return period of 5 years. And so for plant number 1, the time series flow was 25.5 kilolitres per second, as opposed to the event space, which is 27.7 kilolitres per second, and plant 2 was 31.7 versus 32. And so whilst the numbers are very similar, I think if you're at the plant, if you're dealing with you know 2.2 kilolitres a second less flow, it's probably a little bit easier to manage. And so yeah. And so the main difference there was that there was a slight difference in the peak flow rates into the plant, and that's sort of one of the things that the treatment plant guys need to understand where the peak flows will be for an actual event as opposed to a design rainfall event based assessment. All right, next slide. Yep. I think that's it. So that's a bit of a summary of quite a lot of work, and I've just sort of given you a bit of a snapshot of what we did and what some of the outcomes were.
That's a substantial project. Yeah, we've had a few more questions come in. Jonathan, could you explain the grid rainfall data method, and is it available for now modeling like calibration?
So the grid model method. So we didn't actually produce that grid method ourselves. That was done by others from the Bureau rainfall, and it was then processed down from as I mentioned earlier, from the daily records using some of the tipping bucket information to produce half-hourly intervals. So I suppose that a key thing to point out there is that when you're going down to only half-hour timing intervals on a sort of smaller network, which is including your retic and stuff, your half-hour time increment might not be as appropriate to use for a shorter duration event. And so yeah, there could be some limitations on that one. But yeah, so we didn't produce that data ourselves. So I don't know whether it would be available for general use, but I probably wouldn't use it as a starting point for calibration.
Okay, this one's a bit of a long-winded one. Did you just use Melbourne Water-owned network, or you added some elements of retailers' networks as well? The reason for this question is there are a number of sewer flow control facilities and other infrastructure which may affect the flow patterns in Melbourne Water mains. Was this a consideration to your study?
Yes, or I suppose yes and no. So we do include some elements of the retailer network in the Melbourne Water model, but again, some of the details around some of the flow control facilities up in the retailer network. Some of them are included, but the individual sort of operations on any particular store may not have been included. And then I suppose we're going back sort of 50 years, and some of these flow control facilities probably didn't exist for some of the storms that we simulated. And so the representative result is that some of those flow control facilities possibly weren't constructed when the rainfall actually fell.
Okay, this one's relevant to kind of severe weather that's been occurring. You mentioned including events with ERS spills. Is there ongoing monitoring to inform ERS spills in the network?
Yep. Yeah. So the ERSs are all monitored for level and when they operate. So I suppose the short answer is yes, there is monitoring on all those ERSs to inform when they operate.
Okay. So I'm just going to spend a few minutes covering three different aspects of the software when in your project work you have long time series, large data sets, and multiple simulation runs. So we'll still have a few more minutes for Q&A towards the end of the session. One of the questions asked at actually the front end of the webinar was, does ICM have a built-in long time series tool that defines start and stop conditions for discontinuous simulations? Short answer is yes. We put an episode collection function into ICM. So to help you save time and project spend, ICM actually helps you automatically separate out events for you based on exceedance criteria. So you're able to, save time from manually dealing with the events themselves, as well as on the compute time for running these long sequences within your analysis. So here's a brief kind of walkthrough of how to set up the episode collection in the software itself. This is we have the GeoPlan view. There's a model that's been simulated already. We're going to look at a particular location for the purpose of this walkthrough. It's just a single location on the bottom end of the network. We're going to look at the flow for this particular conduit, and we're going to see that there's an exceedance of 40 liters per second or 0.04 meters or cubic meters per second at various times. So we're going to run a sequence or set up our episode, and we start by using the statistics template at that particular location. We're going to assign a threshold of 0.04 cubic meters per second. From there, to set up the episode collection, we build the stats report based on the simulation that's already been run for this particular model. And the statistical report is most commonly used for analyzing outfall of spills, the spill duration, the total volume per spill, are some of the details that are reported. And then each time a user defined threshold is exceeded, the exceedance statistics will include date and time at which the threshold was exceeded and the period for which that exceedance occurred. So all I've done is I've gone into my model group and I've added another episode collection and creatively called it episode collection 2. Within this tool, I've dragged over my statistical report that we just created for that particular part of the network. I establish a lead time and a tail time for those particular events. I select to round it to the nearest 15 minutes. And then as you can see, the episode collection has generated my start and end dates. And then I'm able, from that below graph, to be able to highlight when those particular events are occurring. And I can do kind of a manual review at that part as well. So you can see the results from the statistics template, from the hydraulics, and then the episodes themselves of when those exceedances are occurring. So I'm going to close out of the episode collection, and we're going to create a new simulation. Call it episode collection simulation or run. Drag and drop your episode collection that we just created into your run group. And then pay attention over here. We adjust the simulate runoff only between episodes. So the software is automatically going to, when you're simulating, it's going to differentiate the hydraulics or when you want runoff only between your particular events. Kick off the simulation. This is occurring on my machine. As we know, we could use the distributed computing to offload your sims to a high-spec server, which you'll want to do when you're crunching simulations of this kind. And then you can see it's been separated out within the run group. The RO represents runoff only, and then the separate runs are also where the hydraulics are occurring. So we'll just let the simulations finish up. So again, within the episode collections, you can reference individual episodes as well as apply different hydrologies. So you can use a warm-up of a defined period, the full hydrology for the entire run, hydrology between the episodes, or no hydrology as well. And then once those sims are created, we can go into the model results. And I'm going to select an aspect or a segment of a subset of the total run. So this will plot a result of that original location. And then instead of plotting the entire sequence, this is just demonstrating that that subset was runoff on either side, but where there was no hydraulics occurring. So you can see where the exceedance was happening on that 0.04 cubic meters per second. But the software has represented that, and it's done it with, through various ways, generating the start and end times of your episode collections. So the second major tool that we've talked a fair amount about, if you're talking to anybody from Innovyze with regards to sewer modeling, is the time series database. And it's applicable to these projects because of the long time series data, the large data files, and the multiple data feeds. So as we've seen with Jonathan's particular project, we have an example of 1,000, I think it was 1,020 rainfall grid points that you could potentially want to import. So we have examples with TSDB where 1,000 kind of data points have been linked directly to that time series database. So it's a technology that underpins ICM Live, but it's available to you in your planning models as well in InfoWorks ICM suite. And it allows you to connect directly to your SCADA data. So this is just showing how you can map directly to the data itself in a live fashion. And then on the right side here, when we're dealing with larger data sets, it helps to have that actual data connection. So we can see, hundreds of themes or multiple themes or data stream names that have been linked and then you're automatically able to map it in. So when you're dealing with data sets of this size, it's quite beneficial to be able to map them and have them at your disposal. And again, this helps you reduce errors, save time, and eliminate manual steps when you're dealing with your time series data for this particular for these particular project types. And then the third aspect of ICM that I want to discuss is ICM Exchange, and that provides existing Inforix ICM users with the ability to auto model updates from your asset data, optioneering and scenario analysis, and run sensitivity for actual calibration parameters. So this particular example here is a pump overflow. We have a CSO, and the pump flow is represented. What we want to be able to do is automatically set up using scripts within ICM Exchange to generate multiple simulations and produce results. So for this particular example, you can adjust the capacity of your pump station and figure out the optimal point in which the relief structure is no longer overflowing. So I've kicked off simulations that are running in the background using this particular script. So Exchange is typically used to run batches of simulations with changes coming from outside the software. You don't have to be inside the software to do that. And then it allows you to automate any process open in the software. So right now you can see multiple simulations have been kicked off automatically based on pre-configured criteria. For this example, we want to find that the optimal pump capacity where flowing no longer occurs. So if you look at the target column on those simulations, it's running multiple scenarios of varying capacities for this particular pump station. So you can edit and update query database tree objects, create copy and delete database tree objects, create network scenarios as we've seen here, commit and validate networks, and edit the network objects themselves. So this particular example, it's finishing up running and it'll produce the results, and then it's going to spit this out to a spreadsheet that's going to provide the output of that optimal pump scenario with the relevant capacity. So it's just producing results. And then here it's automatically generated them. The results are going to be available in my model. Click on the one, it's 58 liters per second, and then that's the optimal scenario, and then I can run my analysis from there. So that's ICM Exchange, the time series database, and the episode collections. Okay, we have a few minutes just for a few more questions. Okay, when you have severe rainfall events, as reported in the news and what we've been experienced in the planning world, will this week's events be looked at as an anomaly, or do you see this as a driver for more studies of projects of this nature? Do you see this expediting projects like this, or is it just considered, we anticipate this statistically?
Well, I would say it's, I mean, the people on the news say it's 1 in 100. The hydrologists will probably come up with a different number, but I think everyone can recognise that it's a pretty extreme event, and it's not likely to happen that often. I can't see any sort of water corporations planning for planning their systems to cope with situations like this. That being said, there are sort of off the sort of AR&R 2019, there's sort of there's some indications of some sort of climate change scenarios that you can look at for the future. So you know, you might just sort of tweak your tweak your design storms a little bit to incorporate, you know, maybe the sort of your 18% AEPs, you know, now versus in 20 years might be a little bit different, so you might sort of change them up a bit. But certainly events like this, you would just sort of note that it's fairly extreme, and then yeah, I don't think you'd be doing anything to your network to try and cope with it.
Mm. Can these types of studies be applied to a small to medium-sized council? You know, with urban utilities and Melbourne Water. Can we relate?
Yeah, definitely. So a time series analysis is, you know, it's on the actual rainfall that's fallen in an area, and then you apply it to your current network. So, and it just sort of gives you that sort of, you know, or if you're looking for your compliance limits or your return periods on your spills, or however you're going to analyze your system. So obviously, you know, like with everything, you need to have some good data to be able to feed into it. But yeah, definitely applicable to smaller councils as well.
Mm. Okay. How did you model and calibrate the overflow structures within the floodplain? Did you assume overflow structures will always be available for free flow, or did you apply creek water levels to the model?
So in Brisbane, as I mentioned before, we assumed that they were all open. So best case scenario, and that was a purposeful choice. Obviously, in the calibration project, which precedes this work, we do look at overflow structures where there are flow monitors, and we do our best to actually calibrate. So some in calibration we can see are always operating, so they're not blocked, and other times we see that sometimes they are blocked and sometimes they're not. So at least for my project, we assume that they were always open, but it was based on some form of calibration.
Okay. How long did the 50-year simulation take to run? And what did you run it on?
You go, Nick.
Well, I didn't do 50 years.
Oh, well, I didn't do 50. Yeah. So well, the 50-year hydrology wasn't too bad, and then the or each of the 1 year worth of events took. Yeah, I'm not sure. I couldn't put my finger on a number at the moment, but obviously we sent, you know, 50 different events or 50 different. Oh no, we were doing event-based stuff, so we sent, you know, we break it down into the 92 events. So it's probably a little bit different to a full 50-year sim.
You got to remember, Jonathan's project is on a trunk main, so it's not, you know, relatively speaking, it's not a Brisbane model. So for my model, the simulation, so the longest simulation was a 50-day simulation, and that took about 3 days of runtime. So for my project, I was running about 10 to 15 simulations concurrently, and for each catchment, it took between 2 to 3 weeks to run the full 120 simulations. And we ran that on a 24-core computer. We can run about 40 simulations concurrently if we want. Each time we add more, they slow down. Since doing this project, we've got a few extra computers, each more powerful than the last. So, yep.
Awesome. We're at the top of the hour. I would love to keep going, but we want to be considerate of everybody's time. So all the questions that were submitted, Jonathan and Nicholas will be able to answer them, and we'll distribute those answers out to you. I just wanted to say thanks for joining us. Any questions, yeah, we'll get to you. If you have any feedback or want to present on the next webinar, let us know. Just drop us a line, and we would love to present with you. And special thanks. One that comes to mind is Scott Nichols from the GHD Melbourne team. Special thanks to Urban Utilities, Ian Jennison in particular, with the great work his team does there. And thank you to Melbourne Water. Special thanks to Andy Chan and Nigel Pugh, all for graciously enabling this presentation and conversation to occur today. Nicholas and Jonathan, thank you so much. Well done. And hope everyone has a great day. Take care.
Thank you. Bye.
Thanks, everyone.